The link to the PDF is in the chat, and if you want to repost that later for the new people, feel free to do
Okay.
so.
Okay, and we are now live streaming. So that's an additional way that people can view us. I think we're ready to go. So I'll start the meeting and hand it over to Gary. So welcome everyone to the Ontology Summit 2026. Today is the 18th of March, 2026. And we're very excited to have Pascal Hitzler, who is going to be speaking today. And our chair and host is Gary Burcross, who will now be taking floor.
Yes, I have a few words to say. Thank you for the introduction, Ken. And this is our third session on AI on ontologies. We have one of the former speakers attending again, so it should be an interesting discussion. And as Ken said, we are just very happy to welcome Pascal Hassler back to the Ontology Summit. He's been a frequent speaker and an important speaker, and he's particularly apt to speak today to us this year about this year's summit. Not only the present view of ontologies and AI, which he's been intimately involved in, but also the past and future if he has time. This is reflected in the fact that he was the founding editor-in-chief of the Semantic Web Journal, the leading journal in the field, and is now the founding editor-in-chief of the new Neurosymbolic, artificial intelligence journal. Perhaps even more interesting is the fact that many aspects and issues of the current AI work has long been Pascal's interest, going back to his dissertation, which concerned neural symbolic integration and a very broad view of AI. If you've ever had a chance to talk to Pascal about these things, he has a very interesting and broad view of these topics. Pascal is currently a University Distinguished Professor and endowed Lloyd T. Smith Creativity and Engineering Chair at the Department of Computer Science and Kansas State University. That's a very long description. He directs research at the Institute for Digital Agriculture and Advanced Analytics, the ID3A, and is also director of the Center for Artificial Intelligence and Data Science, the CADS. He serves on many boards, is on the Kansas Legislative AI Task Force and on the Samsung AI Advisory Board. And there's much more about his research record and activities on our site, and even more with a link provided there. His talk today is entitled Some Advances in Neurosymbolic AI Related to Ontologies and Knowledge Graphs. And luckily, Pascal also has some time for Q&A following his talk. With that, let me turn it over to Pascal.
Thanks a lot, Gary, and thanks for not expanding on the additional things. So yeah, it's a pleasure to be here again, and in particular to talk about neurosymbolic AI and ontologies and knowledge graphs. So as Gary alluded to already, neurosymbolic AI is not new. And in fact, I started using the term systematically about 20 years ago, when Arthur Garces, who's in London, and myself started a workshop series on neurosymbolic learning and reasoning. We avoided the term AI because it was AI winter, but of course it was AI, and that ran annually, mostly at some major AI conference, like I don't know, Triple AI, HCAI, ECAI were kind of the main things. We were running it as a workshop. And now it's a conference, of course, 2024. And we kind of kept the community alive. I should say Arthur kept the community alive, mostly because I was mostly doing some web stuff and only a little bit on this. So it's now very exciting, of course, that the topic now suddenly booms up. Because I was always kind of thinking, yeah, this is what the community, one of the things the community really should be doing, looking into merging these two different strands of artificial intelligence that come from the symbolic side. And of course, here being at Ontolog, the ontology and knowledge graph side is firmly on the symbolic side. Of course, often using machine learning methods, but still firmly on the symbolic side. And then the machine learning side, which of course with deep learning has had major strides and successes in the last 10 years, including now bubbling over into the public conscious, of course, with large language models and all the ramifications of that, and us as a research community left to deal with the dynamics and how to deal with that in our field, which I think is a challenge in itself. Anyway, couple of books here. I shared the PDF link to the presentation in the chat. I can actually do this again. For those who are new, in case you want to look up references, etc. I'm going to talk about a mix of different things, essentially. Essentially three topics. The last bullet point here is going to be some musings, which we may come to or not. And I have a lot of material. I can shorten as needed. The idea is that I'll talk about each of the three pieces, and then we'll stop and see if there's questions or discussion. And we just kind of play it by ear. I'm fine doing that. And the first theme will be about deep deductive reasoning and explain what I mean by this. And then I will talk about ontology-based hidden neuron activation analysis, which is one thing we're really digging into in the lab. And then another one which we're digging into in the lab is LLM-based knowledge graph and ontology engineering. And I think all of this should be interesting in the context of this community here. All right, deep deductive reasoning. So this has been bothering me for 20 years, essentially, but there was just no way to tackle it 20 years ago. And the point here is to say, well, if we take deep learning system, just a machine learning system, and would like to see if we can train them to do pure deductive reasoning in the fully logical sense, can we do that? And you may ask, why is this interesting? Well, for me, mostly it's about two things. We have two abstractions of kind of how the human brain works, in a sense. We have the artificial neural networks, we have formal logic. Both of them are abstractions, very different ones. And just kind of to see kind of to what extent can we do one with the other is just a fundamental question for me. This is also a question that you could say comes out of cognitive science. But then there's also engineering questions. If you get it to work, you could use it for dealing with noisy data. You could use it for speed, as symbolic algorithms of very high complexity, for example. But of course, that's all about if you can get it to work. And when deep learning started to hit, and I think it was essentially when alpha chess hit the ground, I thought, okay, we have to look into this because there may be avenues now. The problem setting here is relatively simple. You take a deductive reasoning problem, you take a set of logical formulas, and because I'm a semantic webber, of course, we all did it in a semantic web context here. So take a set of logical formulas, and then every other formula over the same language is either a logical consequence or not a logical consequence. So you can essentially look at this as a classification problem, a binary classification problem in machine learning. And in fact, it is kind of a machine learner's dream because you can produce as much training data as you ever want, because you can just run a reasoner and then see if you can feed it to a system. And in a sense, this is the kind of the dream scenario for the claim you can solve everything using deep learning. You just have to throw more data at the system. Well, let's see if this works, right? So there is also a kind of devious intention on my side, because I was kind of always expecting that there would be limits which we'd encounter. The question is more, when will the limits happen? And of course, there's also theoretical reasons for assuming that there are limits. One of my PhD students is working into this with mathematics that I don't have the time to really understand at this stage. But yeah, there seem to be principled limits, or there can be argumentations made that if you kind of go into X time, it's just not reasonable, right, to learn it perfectly. But then we don't probably need to learn perfectly. You want to do reasonable. So, all right, that's the problem. You can also look at the problem from a slightly different angle, and that's knowledge materialization. Rather than a binary classifier, you rather look at generating all logical consequences. Well, you have to kind of cut it because the set of all logical consequences is generally infinite. So if you want a finite set, you kind of cut by some whatever syntax length or something like that. Still, you can produce as much training data as you want, but this is a harder problem, of course. This is also the one which really would be interesting for applications if you can get it solved, because then you could actually do formal reasoning at scale without having to do it with a formal reason. All right. So, and I'm going to give you just an overview of the results which we had before we dropped the topic. And we dropped the topic because essentially we hit the limit pretty early and are out of ideas and have been out of ideas for quite some while. So, but let me first explain what I really mean by deductive reasoning here, because what I'm interested in is really the formal logical reasoning. So the key column here, well, on the left, there's papers. I'll talk about some of this. We list the logics here. I'll talk about this. The key thing is the transfer column. Generative means, is it materialization? That would be generative, or is it classification? And then scale, of course, and performance. I didn't give numbers here, right? But the interesting column is the transfer column. What do I mean by transfer? By transfer, I mean you train on however much logical formulas and consequences you want, but then you test it on completely different names for predicates and constants. That's the transfer. And everybody knows, well, who knows deductive reasoning, that for deductive reasoning, it doesn't play a role. You can just name your predicates with nonsense terms, and the deductive reasoning still works. It doesn't really matter, right? Now, I believe that you can only claim that a deep learning system has learned to do deductive reasoning is if it can do this transfer. If you can't do this transfer, it hasn't really learned to do the deductive reasoning. It hasn't learned the rules for the reasoning itself. Yeah. So, and that's why the transfer is kind of in a principled sense very important. It may not be so important for practical reasons, but I'll talk about this in a few minutes as well. So the transfer column is really central. Now, you notice that there's a no in the transfer column for most of these here. There's a no here for LTNs, logic tensor networks, as well. They didn't scale. That was one of the first things we tried 8 years ago, 10 years ago. They scaled only to toy size, which is not interesting at all, of course. So there is one at the top here where we have a transfer yes. That's work my then PhD student Monir Ibrahimi has done. And this worked. This was really nice. So this used RDFS, which, yes, is a logic, although it kind of isn't. It is formally, you can say it's a logic, but it's a really, really sad logic. Let's put it that way, from a knowledge representation perspective. But that was the first thing we looked at. She made a deep learning architecture which used memory networks, but she did a lot of kind of manual stuff there to get it to work. But then she got it to work for what I called here moderate scale. Our input sizes were 1,000 triples. And then the system really worked well. That really worked. That was really cool. Yeah, for 1,000 triples. And then we thought we were really getting excited. So, and next we tried EL, and it completely fell apart. Now, EL is still polynomial in the terms of the reasoning you look at, but it's a more complicated logic. It's also it's a different polynomial, I believe, in terms of complexity. And one of the things you can see is that if you actually parallelize reasoning over RDFS, then with 1,000 triples, you can get at most reasoning lengths of 10 steps if you parallelize the reasoning as much as you want. With EL, you can make arbitrary long chains, in a sense, or very long ones anyway. So, there is a difference, and that the polynomial is different. We did not manage to get it to do for EL. We tried different ways how to do it for EL. And we kind of didn't really get there. Then the last thing she did before graduating was using a completely different approach, which was used for solving this, for doing the traveling salesman problem in a different setting, which was pointer networks. And that's the lower piece, right? This was with generative with transfer now. We really wanted to get this done, at least for RDFS. And what turned out was that it worked really well on a token basis. We had to put the identifiers, cut them into tokens. It worked well on a token basis. But we could not recover the triples. So if you recovered the triples, there were still too many mistakes that essentially we got garbage. We were not able to salvage that. Perhaps there's a way to salvage it, but we didn't find one. And she had graduated by that stage as well. So, perhaps she may have found a way. I don't know. In the end, we gave up, right? And yeah, there's principled ways to look at this problem and just say there's too much difference between deductive reasoning, the symbolic world, and the continuous world. But yeah, that's where we are. And that's kind of the story here, really, right? So kind of if anybody throws at me, just give more data to a deep learning system and you'll solve whatever you want. This is my first reply, right? Try this, right? We didn't get it to work. All right. So, and now, of course, where can you go from there? And of course, if you don't require transfer, you can do stuff. You have to find good situations where this actually makes sense and gives you added value. But that's not kind of what we were interested here. But as soon as you're closer to common sense reasoning, you can do some things here. There's interesting work going on in Amsterdam. I recently talked with a PhD student from there who's looking at natural language reasoning problems, for example, doing that with LLMs. That's tricky enough, right? So he's also looking at neurosymbolic approaches, how to kind of recover from the mistakes they make and so on. One of the things I find particularly interesting now talking neurosymbolic is situations where finding solutions to a formal logic problem is high complexity, but checking solutions is low complexity. Because in these cases, what you could do is you could use, for example, an LLM or some other system to find solution candidates for you quickly based on training. After training, quickly, the training isn't quick, but after training. And then use a formal reasoner to check on solution, whether any of the solution candidates actually is a solution. This has been done, for example, with LLMs in planning already, but that should carry over to other situations as well. And I have some results here that indicate that can be done. Now, what we've done here was looking at a very old benchmark. Which was came out of inductive logic programming, and of course there's concept induction as an approach for inductive logic programming carried over to description logic, so ontology logics. And the old benchmark is the family benchmark you may be familiar with if you have ever dabbled in ILP. Essentially now formulated, in natural language, so to say, is you take family relationships and information like Dora is female, has a child Rosanna, Rosanna has a child Valentina, Luigi is male, and so on. And you take lots of these examples, of course, and then there's nothing which defines grandmother in this database, right? And then you say, well, Dora is a grandmother, Luigi and Maria are not grandmothers. So you give more examples, of course. And then you ask the system to generate a definition of grandmother, a logical formula that defines, a class expression that defines grandmother based on these examples. That is the concept induction problem in a nutshell. And there's applications in ontology engineering. Jens Lehmann has done quite a bit of work on that. So this you can post to an LLM, of course, and see how it does. And we did that about half a year ago, a little bit longer now, 9 months. A student at Rita Barua did that. And the question is asked, well, the systems we looked at, GPT-4o and O3 Mini, which is kind of a reasoning model, as they call them, they did really well on those, right? Kind of 9 correct, 0 incorrect. These are small benchmarks. They're kind of, I don't know, 40 years old or something like that, right? So, but then we did something nasty. We flipped genders. Of course, this benchmark, well, like sadly so often, is very kind of binary stereotypical gender-wise. And then we just flipped genders of people. So we said Dora is male and Luigi is female and things like that, which is counterfactual in a sense with respect to the mainstream data the LLM was trained on, right? Because most of the data it has would probably say Maria is female. and not Maria is male. So in this sense, it's counterfactual, or you could say it's kind of drowned out by most of the training data. And when we flipped the gender, the LLM got really confused. No surprise here, right? So is it doing deductive reasoning? Well, it's taking our input, but it's also kind of mixing in a lot of common sense stuff, which kind of confuses the system. But then, of course, what we can do is we can use, because constant deduction is really expensive in terms of complexity. So what we can do now is we can take the response it gives and feed it back into a formal reasoner, a deductive reasoner, and check whether the solution is correct. And if not, feed that back to the LLM and then do some iterations, right? Like do you, if you work with the LLM to get the responses you kind of hope to get. But we can automate this process. And we just did 3 loops here and got really better. O3 Mini with at max 3 loops, we got it down to 9.0 or to 7.2 on GPT-4o. So that helps, right? But that's a kind of, I would say, a kind of poster child neurosymbolic approach, right? You use an LLM for speed, and then you do some checking afterwards. Of course, you need to kind of adjust that to application situations. One of the other interesting observations here, which I want to share, is that now, half a year later, LLMs do much better on these, even with the gender flips. And of course, one of the things we don't know is what on earth happened. Why are they suddenly better? The indications we have and we're looking into is that they didn't necessarily get better at reasoning, because while they are doing better on this now, as soon as we give them some more challenging issues which need deeper reasoning, so to say, and they're still not commonsensical, they still make mistakes, right? So kind of they're patching holes, which is kind of what we see anyway. You kind of find a new issue for it, where the LLM chokes some logic puzzle or whatever, which you modify. And then a few months later, it's patched. And one of the sad things, of course, is that we have no idea how they're patching them. We are kind of working with a system that's not only by sheer nature a black box because it's an artificial network, but we also really don't know what they're doing around it, right? To what extent do they actually do everything as an LLM, or program guardrails around, or fork a problem at some stage into a reasoner by doing syntax conversions, which LLMs do really well. You just don't know, right? And that's research-wise a really unsatisfactory situation. Also kind of tricky how to deal with this long term, because we don't know what's going on. By the way, Randy, I saw your question, but I wanted to get this part done first, because that was part 1. So I'm going to read Randy questions, and if you have some, then please also you can put them in the chat or ask them now before I move on to the second theme, because that was kind of what I wanted to talk on deductive reasoning.
Thanks, Pascal.
Randy.
I post them so I don't forget to ask them, so no pressure on time. Thank you.
All right, cool. So you asked the question arising from this one of training the deep learning to do deductive reasoning also emerges from the Dan Kahneman System 1, System 2 thinking. Can System 2 thinking emerge from System 1 processing? Yeah, if you want to follow that classification, which of course makes high level sense. Yeah, and I mean in game we don't know, right? It kind of, yeah, it's probably a philosophical stance whether anybody thinks that higher level features can emerge from the kind of more lower level processing, right? That easily. I recently read a very nice paper actually on this exact question, looking at it from a Habermasian perspective, which I found rather interesting. And really, I'm no philosopher, and what do I know about Habermas? But they kind of took the argument pretty much apart, and said that's kind of very difficult to argue philosophically, for what that's worth. So, but anyway, more questions, please, if
Well,
on the first part.
just related to that question, I think that what the results that you're getting in this hard work exercise of trying to rebuild logical reasoning in that way shows that for example, a recent paper by a colleague of mine, Dale Sherman's at Google Brain and at Amy in Alberta, showed the conditions under which transformers are Turing complete. That in itself is not that interesting. But what I think your work demonstrates is that it's the structure of the knowledge created and retained that enables the improved performance, not anything in the basic mechanism of what's computable or not. And I think that that's a nice direction that this work shows is says focus on the capture and use of knowledge to accelerate the performance in this way, because the bottom line on the Turing computability is the same. So there must be something added as the secret sauce, which my perspective has always been the capture articulation of knowledge. So I think that's the direction you're showing empirical evidence for.
Yeah. So one of the things I learned from my student Joseph Zaluski, who's actually looking at kind of what can you do in terms of complexity of deep learning systems is that's tricky. I'd be very interesting to see that paper, by the way. I'll try to find it, but if there's a pointer, I'd be very happy because I think he'd be interested unless he knows it already.
Okay, I'll send you a link to it independently of this.
Yeah, right. Yeah. So I mean, just my naive musings here on this is, of course, that you can't get Turing completeness unless you have some loops in the system. So you kind of you need those because otherwise you don't get arbitrary depth, right? And of course that is really an issue. A principled issue also for training and stuff like that. If you restrict to feed-forward systems only, then it seems that's the indication I learned from Joseph is that you very quickly run into kind of you would need to blow up your network exponentially in the size of the input logic for it to make sense, right? And that's just a nonsensical assumption. So kind of saying you can do reasonable size or large size systems by training a deep learning system to do them perfectly is just not working. But of course, it's difficult to talk about approximating, right? Which may be helpful at some stage. But sometimes it's helpful to just tell the machine learning people, right, that in a sense, when they're tackling symbolic problems, natively symbolic problems, they're essentially trying to approximate the solution of a problem by means which essentially are kind of almost proven to not be adequate to fully solve the problem. Right? You're approximating a solution with a method of which you know that it cannot fully solve the problem. And you just need to kind of see what you're doing here, right? So it doesn't mean it doesn't make sense, right? But still. So thanks a lot for the oh yeah, I remember seeing that paper. I haven't read it. Thanks a lot, Randy.
Okay.
All right. I'll move on unless somebody else has a question immediately. So all right, thanks a lot. So all right, theme 2. Ontology-based hidden neuron activation analysis. This is something we actually started very slowly 10 years ago. It turned out to be much more tricky than we thought. But it's still continuing, and we didn't hit a brick wall like with the other one here. It's still humming. But it's also hard going. By the way, this is one of the things I learned about neurosymbolic over the last 20 years or so. Neurosymbolic's hard. In particular, tackling some of the deeper issues is hard. Of course, there's always pieces that are easier. Ragging is easy. But then you have ragging, right? So you're interested in new methods, they're hard. All right. So what do we do here? The scenario we looked at was CNNs. It was the first one we tried. And it was the natural candidate. So what's the high level thing that we're trying to do? We're trying to make sense of hidden neuron activations. So it's a little bit kind of, you could say, a little bit like what some neuroscientists try to do with the human brain, right? They're looking at kind of areas of the brain, or sometimes even at single neurons. They can do that in the meantime, and see kind of what do they respond to. I think there was some story, I don't know to what extent it was overblown, about the Jennifer Aniston neuron, right? That kind of only fires if somebody sees a Jennifer Aniston uh, image, right? Kind of that's the dream scenario. Often that won't be the case like that, of course. It will be more, perhaps a region or some patterns and so the human brain. But essentially, that's the kind of driving high-level motivation for this type of work. So where did we start? We of course started with a setting where we thought, okay, we're going to find something simply because there was already work out there which kind of indicated that we may find something here, and that was in the so-called dense layer, in a later layer in a convolutional neural network. So there was other work, in particular, which had to do with so-called kind of heat maps, which indicated that, yeah, neurons in here, even individual neurons, which was easier to analyze to start with. You can also do it for sets, of course. We did some of that, but not too much yet. Individual neurons sometimes just react to specific things on the input image. But we wanted to use different methods because the kind of the naive way of doing that is you just take candidate things you're looking for, like whatever, Jennifer Aniston, right? And you check the neuron whether it responds to Jennifer Aniston part of the picture or not. But of course, that means that we have a reasonably small set of hypotheses what may be represented. And that's probably not how you want to get at that. You want a method that can scale to many, many more hypotheses because we don't know what these things do inside. So why should the human come up with the things, right? You want a large set of things to test for. And for this we use concept induction. I already mentioned that, right? In the last piece, the thing with the family benchmark, which we adjusted. So the same thing used here. So what's the general workflow we use? The general workflow is the following. We were working in a scene recognition scenario. So essentially taking a data set, it was the 8020K data set, which is about over 20,000 images from different scenes. And we took the 10 scenes for which we had the most images. Like, for example, mountain pictures. I don't think actually we took mountain pictures because there were only a few. So, but this ended up on the early example, so I still use the slide. We trained a CNN to recognize these scenes reasonably well. And then we looked at the hidden neurons. And then essentially we can distinguish images that fire this neuron and that don't fire this neuron, giving kind of thresholds above 80% of average of the firing range and below 20% of the activation range, something like that. Positive and negative instances. So images that fire the neuron, images that don't fire the neuron. And then we made use of something the 8820K dataset has, namely it has human-made object annotations on the images. We had not fed those to the CNN. The CNN really saw only the pixels, nothing else than the pixels. But we used these object annotations for our analysis. We mapped these object annotations into a really large class hierarchy with over 2 million classes, which we had extracted and then curated, very crudely curated, from the Wikipedia category hierarchy. And yes, the ontologists here will say, that's not a class hierarchy. No, it isn't. But, there's a lot of uncertainty here anyway, so that seemed to be a reasonable thing to do. To be honest, we tried with Sumo first. Sumo didn't work. It just didn't have enough stuff. Sumo had at that stage about 25,000. It wasn't large enough. So we tried with the Wikipedia category hierarchy, roughly curated. All right, and then we essentially had the input for our concept induction system. So we had positive and negative examples, like the things that are grandmothers, the things that are not grandmothers in the previous one. We had the background theory as well. That was the large class hierarchy. We needed to use an approximate concept deduction system, which was one we had ourselves. It was the easy system, which one of my students had published at AAAI 2017 or something like that. Because a kind of sounding complete system like DL Learner, Jens Lehmann's, didn't scale well enough to 2 billion class hierarchy. And then we gave it the positive and negative instances. It came back with, description logic concepts. Most of them were single classes from the class hierarchy, not all of them. Some were conjunctions. The easy system can't do more complex ones than just conjunctions. And these were our hypotheses for what the neuron responds to, essentially. But of course, then we need to check kind of, are they really kind of, is this because this was just a hypothesis that came out of the system. Now, first thing to note is that the system, the concept deduction system doesn't give us one response. It gives us responses, which, because there is no perfect solution in most of these cases, it gives us a list ranked by some accuracy score. And the top results are often very close together. But we just took the first result. We were just looking, do we have a signal? Does it work? And the naive approach has actually worked here. We did not fiddle with this stuff. That's just how we did it, and it worked. Well, to the extent I'm going to show you. So again, this is the example. Now, this is the workflow. 80/20K data set. We have a train system. We analyze a train system, unmodified train system. And then we separate these images into positive and negative images based on one target neuron, like neuron 1. It was actually neuron 1 in our system, so the second neuron. We have positive and negative images, those that fire the neuron, those that don't fire the neuron. This is really example images for that neuron. And then we ask concept deduction. Concept deduction system says, well, the distinguishing thing is there's a crosswalk on the images that fire the neuron, and there's no crosswalk on the images that don't fire the neuron. And then we want to test whether that's really the case. So we wanted more crosswalk pictures. And since 80/20K just didn't have enough stuff, we just used Google image search to get us crosswalk images in the same image format, which we needed with, I believe, JPEGs. I'm not entirely sure. And then we got on the right Google image pictures, and then we tested whether they activate the neuron more than other images. And if it did, kind of with, I think, over 80% accuracy, then we considered the label confirmed, right? So then we had our hypotheses. These were now the kind of confirmed, well, these were the confirmed labels, right? There were 64 neurons in the dense layer. The boldface ones here are the confirmed ones. So these are the ones which are activated by 80% or more of the crosswalk retrieved images for neuron 1, right? That's kind of, we made the cutoff at 80%. That's all kind of arbitrary, right? We just wanted to see if we get a signal, cut off at 80%. So we got, I think, a total of 24 confirmed hypotheses that way. And then, of course, last thing you want to do is a statistical analysis. So each row here, let's go back to neuron 1. This row is a hypothesis. The hypothesis is that neuron 1 activates more strongly for crosswalk images than for other images. And now we have something we can statistically test. And that's what we did. And these are the 24 hypotheses, confirmed hypotheses that we wanted to test statistically. And it turns out that we could confirm 19 of those with a really low p-value. So that was a statistical analysis. And that worked out really well, right? We got 19 confirmed neurons. Like we really have a very strong indicator now that neuron 1 activates more strongly for crosswalk images than for whatever quasi-randomly picked other images. And that's cool, of course, but the work here only begins. And I'm going to tell you about a little bit of the things that we found. So one of the things which I found interesting was digging deeper here now. And this stays with the neuron 1 example. We were looking at type 1 and type 2 errors. So one of the things was images we retrieved from Google Images, which had crosswalk, which were retrieved using the crosswalk search term, which did not activate the neuron. And these are typical examples for those. And there's an interesting thing here. 5 of these 6 examples here are actually synthetic. They're computer graphics. Now, 80/20K doesn't have computer graphics. So this is kind of interesting. So it seems that it doesn't react to crosswalk. It reacts to natural crosswalk photos. which of course raised one of the questions, can we use that for fake image analysis? Well, we're looking into that, don't have results yet. The button on the bottom right is also interesting because I think you need to be in the US to know that this is a crosswalk, because it doesn't show the crosswalk, it only shows the sign for a crosswalk, right? So this is also interesting. On the right, there's images that were retrieved using other keywords, which still activated neuron 1. The one in the bottom middle probably has a crosswalk, not entirely sure, right? So that's kind of okay. We just retrieved it using a different keyword. And the other interesting thing here is that a lot of these pictures seem to show bushes, greenery around the road. And I mentioned earlier that concept deduction doesn't give you one response; it gives you several. And in fact, for neuron 1, the second response from the system, actually, the second response also was crosswalk with a different spelling. But the third response then was bushes, bush, with actually an accuracy score from the concept deduction system, which was essentially almost as high as the one for crosswalk. So that was interesting. So, you know, even the I believe that's the type 2 error here, even those seem to be making sense once we dig deeper. That all is very, very encouraging, of course. We did something else. We checked what about not using concept deduction? Because concept deduction is really expensive. You have to build the background knowledge, you have to have a concept deduction system that scales, and it still takes ages if you run it with a 2 million, just the class hierarchy and so on. So we checked what happens if we don't use a concept deduction system, but just use the same terms, positive and negative examples, which we feed to the concept deduction system, and just give it to a large language model, GPT. And it actually kind of worked as well. It gave us, you know, again, hypotheses, which we could check on with our pipeline. The difference is that it only gave us 12 confirmed, statistically confirmed labels, while concept deduction gave us 18. So that's kind of interesting. I don't know exactly what goes on there. We can hypothesize, right? But yeah, so in a sense, we could use a large language model here as a quicker check. Do we have a signal? And then do a real analysis with the concept deduction system to get stronger results, perhaps. That's all in the making on our side. In the meantime, we carried this over to other classes from the ADE20K dataset. Some of these classes have very few example images. And there was a degrading performance the fewer example images we had, but it kind of worked even kind of at kind of more to detail than I thought it would. So that was encouraging. We tried with a different scene recognition test benchmark, Sun 2012, and essentially replicated the experiment in the different setting with pretty much the same results. Some differences, I believe, in the workflow here. And then we also have positive results for text classification using an LSTM. That was a KPAP paper last year. So that also worked in a completely different setting. That's all very encouraging, and work is going on. I want to briefly mention that we also looked at whether the labels that are being generated, and this is again the ADA20K setting, actually make sense for humans. Because one of the applications here is explainability, explainable AI. So you want labels that make sense for humans. There was a big Amazon Mechanical Turk experiment, which was done before LLMs hit the ground. So there were no LLMs here in the picture yet at that stage. Essentially, we did pretty similar thing to what the concept deduction system would do. We took two sets of images and then took keywords, and one of them, say, is concept deduction system generated the top results. One of them is generated by a quasi-random procedure, and one was generated by humans. And then essentially ask which of those kind of fits which image better, right? That's kind of the Amazon Mechanical Turk setting. And if we did that, then what we got was that human-generated labels were still much kind of clearer for humans, but the concept induction generated labels were still much clearer than the quasi-random ones. It's probably not an unexpected result, but you have to kind of look at these things. And then sometime later, after LLMs hit, we of course did the same thing with LLMs generating the labels, which we already know doesn't give us as many confirmed labels, but still does a reasonable job. And the result here is that in terms of does the label make sense for humans? The LLM is between the human-generated labels and the concept induction-generated labels. So you get a nice trade-off here. The LLM gives you labels that make more sense for humans, but the concept induction-generated labels give you labels that you can technically confirm more often. So there's a nice trade-off here. All of that, of course, just opens up more questions, which is exactly what you want. All right, I stop on this piece here, and asking if there's questions. Otherwise, I'll move on.
No question, but I want to compliment you on the work regarding demonstrating these empirical things, because I think that the whole cascade of tougher learning problems like concept learning are an essential part to fill the mysterious gap that we've all sort of acknowledged between the neural systems and symbolic systems. So I really like the ideas between there. Thank you.
Yeah. I will probably come to, if I manage to get to the short last part. It talks a little bit about human in the loop and the importance of that. So absolutely.
Well, now we have two
Harshit.
raised hands.
Yeah, Harshit, please.
Yeah, so I have one question regarding are we looking for a meta classification on which we can actually do a projection from a surface level, we can take any surface level input text in any natural language, and then we can project that into a very specific category, and then call it a frame, and we can then train that frame, because we can actually, once we classify that, okay, these are the meta level frames on which any incoming surface level has to be projected into, and then try to train on the language level. Because what I have seen is, if traditional neural network is good at classification, and if we have a, let's say, I'm giving this example because I have been searching around Sanskrit Panini based grammar, which actually uses 6 set of classification, which is in language, actually it is called patient, location, instruments. These are the 6 categories which is being classified. So why can't we actually use any natural language text to actually project that into the these category, and then try to train on this, considering these are the meta categories?
Yeah. So let me put it that way, right? That sounds really interesting. So there's just a lot of questions that open up here. I presume what you were just asking was in the context of large language models, right? And large language model understanding. Is that correct?
Yes.
Yeah, so
naturally, actually, sorry for cutting. Actually, I'm expecting this process to be generalized across the all symbolic domains, not just natural language, but the coding, any mathematical domain. Every domain could be actually then reprojected. Like, we can use the natural language to actually translate that into a natural language. Use the LLMs to actually translate the symbolic into the natural language, and then whatever we get, in a simple description, let's say we take a fx square, like a function, and then ask a LLM to write the description in English, and then you apply the projection from the English to the meta frame, what we call a 6 categories based on the Pani, and then train that frames. I use that frames to train the LLMs for classification.
Yeah. Just saying, I mean, but why not? Right? The world is open here. This observation here, opens so many possibilities. And of course, one of the things, kind of generalizing a little bit from your idea, is, and this is one of the thoughts here, of course, that you may want to use the analysis here to to program against it in some way, you know, and you were suggesting some ideas here already, right? It could also be a purely symbolic system that does that, right? It does something with that to essentially fact check on the thing. What kind of if you have a road picture, right? And you know, the hidden layer says, well, you found a kangaroo. And you know this is a North American setting. Think of a autonomous vehicle, right? Then that's probably very unlikely, which is something you may be able to catch with a symbolic system even, right? Or with some other system, you know, to kind of catch mistakes and catch errors. That's kind of part of the idea, which goes a little bit beyond just human level explainability. And there's of course more complex workflows you could think around that. You know, so absolutely right. I see that the options are wide open here. So thanks a lot. Yeah. John. And you're muted in case you're trying to say something.
I think actually Ravi was next.
Oh, yeah, but I don't see the hand up any longer. So,
Oh, okay.
Yeah,
Okay.
but then,
Well,
oh, it was Ravi. Okay, Ravi.
just wanted to know that the case where the concept helped you more accurate descriptions, would that be better amenable to further machine analysis?
That is our hypothesis right now, and in particular, we are interested in going beyond just the heuristic system, because deep description logic, concept induction, if you kind of use a system like the learner, the enslavement system, it can actually give you complex logical expressions as labels for neuron activation. And of course, you also don't want to look at just one neuron, but also at ensembles of neuron and so on. And one of the things we'd be interested in is going exactly that direction, getting the complex logical expressions, which you can then kind of post-process using some knowledge-based system. So that's an idea, but again, that's a high-level idea at this stage. So we need to kind of make this work. So yeah, cool. All right, John. So one more question, then I'll move on.
Okay. Well, I'd like to raise a point about deep deductive reasoning. It's true that if you have a theorem prover that doesn't know how to select the next thing to check, the deep deductive reasoning can be very, very slow. On the other hand, if you have a system in which there's a very much more context-related method for selecting which options to check next, you can have very, very rapid, deep deductive reasoning, even with immense amounts of knowledge, provided that you have a way of finding the relative knowledge very, very quickly. And that's the kind of thing that we had been doing with our computer systems. We had VivoMind, which was purely symbolic and had immensely powerful search mechanisms for doing reasoning within a huge amount of data. It would find the correct things the most likely things to find and process very quickly. And our current system called Permion combines the LLMs for doing the kind of things that LLMs can do, but they combine that with the deep deductive reasoning. That's a very powerful combination. And so I do make that point that you can indeed do deduction very fast if you have a proper way of finding the data you need to reason with.
Yeah, thanks, Son. And that's good to say. So of course I was presenting a very kind of narrow lab problem here, but as soon as you kind of open up to more options of combining neural systems and symbolic systems and letting them intertwine, that there's very, very interesting, practically relevant results to be had. So thanks a lot for the comment. Excellent. All right. Gary, your comment, you might say that LMs can provide some version of background knowledge as text to use as a frame based on its vector space neighborhood. Yeah, right. Yeah. Yes. I think I'll move on, but yeah, it just opens up so many questions. So thanks a lot, everybody. So the last piece really, because the fourth bullet point here is just a few minor musings. So this is about LLM-based knowledge graph and ontology engineering, and there's a bit of a steamroller coming here. And I want to kind of tell you what we found there so far. So what exactly is coming? What am I talking about here? So what I mean in this particular case, LLMs for knowledge graph and ontology engineering, is looking at hard knowledge graph and ontology engineering problems that have been known to be hard, involving a lot of human expert time and so on, and have been very, very hard or essentially elusive to automate. But that are central to knowledge graph and ontology development, maintenance, and etc. And talking about things like ontology modeling itself at high quality, which of course is a difficult notion by itself, but everybody has their idea what high quality is. Take your notion, and it's difficult to automate that, right? Unless you say we don't care about quality. In some cases, that also makes sense. So, and related to that, also ontology extension, modification. These are hard things as soon as your ontology becomes complex, and you wanna keep a high quality standard. Ontology population is another thing. Of course, that's also just generally database schema population, database population. Usually done based on text, but also, of course, relevant to do it from other sources. But that's the main thing that's usually looked at here. That's actually construction of the graph complying with a schema which is given by the ontology. So that's the perspective on the ontology here. Again, automating, very hard. Human, yes, if the human really understands the ontology, then the human can program this to a certain extent, but from a database, for example. But from text, that's still kind of very tricky. It's something a human can do, but automating, even scripting, is hard. Ontology alignment is another one. That is kind of mapping between two schemas, and not talking about the simple one. I'll talk more about this in a second. It's going to be my main example. I'm not talking about one. Is this class in this ontology the same as this class in the other one? I'm talking about complex mappings, which are really what you practically need. I'll talk about that in a second. Very hard problem. There's benchmarks. Yeah, I'll talk about this. There's also something called entity disambiguation, co-reference resolutions. Are the two things actually the same, or is the thing called the same actually two different things? This is kind of one of the things that is sometimes just killing data integration efforts, because it can be so hard, and essentially needs to be scripted for each situation. And if you have a database full of, say, scholarly publications written by Chinese people, it's almost impossible, right? As long as you have other, because the kind of the names there have a lot of redundancy, so it's really, really, really hard, for example. All right. The conjecture here is that a specific type of ontology modules, and I'll talk about what I mean with that, will help and is helping with knowledge graph ontology engineering tasks, both for humans and for automation. That's a driving hypothesis which Kogen Shimizu and myself have, so we're kind of driving this. And let me tell you what modules are in our sense. So this comes out of an effort many years ago. So let me tell you a little story here. Kogen came as an undergrad into my lab, and when he became a grad student, we kind of talked about so what should he do? What does he want to do? And he said, I would like to automate ontology modeling. And then I said, I'm absolutely fascinated with that, right? And that was before LLMs. That was whatever, 10 years ago or 8 or something. But I said, before we do that, let's get a better handle on how humans do it, but let's do it with an eye on future automation. And that's what we did. And what came out of this was what we call the modular ontology engineering methodology, MOMO. And central to this is modularization. So, and in a specific way. What you see here on this image is a visualization of an example. Well, our ontology modeling process, which I will not dig into in detail, uses a specific type of schema diagram, a visualization of essentially possible relations between classes as a main vehicle to talk with domain experts. It's essentially almost the only vehicle other than natural language that we use to interact with the domain experts. So, and it is made to be pretty intuitively understandable. So essentially you have, this is a little bit of some work we did with NIST on supply chains. And for example, event provides role, participant role, right? So between event and participant role, which are classes, you can have a relation called provides role, for example. That's all it says here. It doesn't say that anything about domain or range, right? Because provides role may also be elsewhere. So it doesn't really speak directly to the logical axioms, but you can use this to talk in natural language with your domain experts and, that way figure out the logical axioms. In the background, there's still a logical axiomatization, but it doesn't show up here in this diagram because you don't want to overload the diagram, right? You want to put the text into natural language. The arrows with the white arrowheads are actually subclass relations. That's the only other thing we use here. And then the colors are, well, the kind of orangey color is classes. The yellow ones, oval ones are data types, like string. The purple ones are controlled vocabularies, where we want them. And then the blue dashed ones are, well, that is a module. Something complex may be here, which currently we're not modeling, or which may be modeled elsewhere in the diagram, essentially. And these big boxes here around a part of the diagram are modules. Well, the modules actually consist of all the logical axioms, because the ontology consists of logical axioms and not of drawings. But essentially, it groups certain things together into a module. And what do we want of a module? Our requirements are soft. What we want of a module is we want a grouping of things that make sense for an expert as the things most relevant to a key notion. Like, for example, to a trajectory or to an event in this context, or to a container. This is supply chain, right? What are the things you want for a container? You want a container class. You may want a contained in relation, which connects, in this case, there's reasons for that. I don't want to go into detail. Events, transportation events with traceable resource units. You want some time that's related to the container, which talks about when things are in the container, and you want container types. That's the minimal things we wanted here, right? So these things together become the container module. The main thing really here is that this is not a logical notion or a structural notion. It is a purely human conceptual notion. As such, it's also fuzzy. Modules can overlap, they can be nested, as you see in the bottom right, and so on. And the claim really is that an ontology that comes modularized in this way just makes essentially almost all the ontology engineering tasks where a human is involved easier down the line. Why? Because it resonates with the human conceptualization. If you want to change something that relates to container, you look in the container module, right? You know where to look. If you structure your documentation that way, right, then you understand what's going on much more easily than if I would do what's usual in this case, right? You don't have them, and you have the pieces that belong together distributed all over the place, right, with arrows going in all corners. You can't even trace the diagram in that case. And if you just have what you often so have is a list of classes and their relationships kind of frame-like, and then you even have 2 or 3 dozen classes, understanding what's going on is really, really hard, right? Well, a diagram like this, is just an easy entry point. If you do ontology population, right, you get things evaded to an event, you know where to look at. The diagram even tells you the structure of the underlying graph, so you can directly do the scripting based on the diagram. Of course, you have to post-check whether you violate any axioms. But essentially, it helps you if you want to make a Sparkle query, because the diagram gives you the structure, and the modules tell you where to look for things. that kind of conceptually belong together. So the claim here is that it helps. And yeah, we have some preliminary results also with human experiments that it does help. So, but here's the other thing. When we developed all of this, it was already with an eye to automation, and that was before LLMs hit. And then LLMs hit, and of course the claim is still the same. This will also help LLMs. And interestingly, what I just explained should work for LLMs. Why? Because LLMs are trained on human texts. So if groupings, a divide and conquer approach, which modularization essentially is, if you make a divide and conquer approach that helps humans do things more easily because you break it down into pieces that are easier for the human to work with, then this should do the same for LLMs. You break the big problem, the big monolithic ontology, into smaller pieces, and that way help the LLM to focus on the sub-problems. So, and now I'm going a little bit ahead to part 4, the small one, right? Humans are really good at breaking down a big problem into small ones. LLMs are not. That's why structured prompting is so helpful. The human does the breaking down into problems, right? And then gives the sub-problem to the LLM, for example, right? This is also a big issue, I believe, in all this kind of agentic craze right now, because breaking down a big problem into sub-problems that it makes sense, that's a hard problem, right? Humans are good at that. The LLMs, well, perhaps in some situations. But this is tricky. I'll come a little bit more to that in a bit. So anyway, that's the idea. That's the promise, what I said regarding using LLMs for this. This, by the way, is again a diagram of a different ontology we did, which was the enslaved ontology. You can look it up on enslaved.org, the system we built with some historians on the history of the Atlantic slave trade. Again, you see the modules here. We don't need to look into more detail here. Some pieces here, like for example, in this enslaved ontology, we have agents, which, for example, can be people. And then, for example, out of the historic records, we get the record of origin, where they come from, or the ethnic group they come from, information about their race according to the old record, and so on, about age, stuff like that. All right. So, I told you the conjecture already. The conjecture is modularity helps to do LLM-assisted knowledge graph and ontology engineering. And I want to show you results, particularly with respect to one, because that's the most mature we have, with respect to complex ontology alignment. So let me talk about this as a key ontology engineering class. The setting is the following. You have 2 or more knowledge graphs whose underlying ontologies are different. They may be very different, but in terms of topic, they're overlapping or highly overlapping. They may be talking about the same thing or overlapping about the same thing. And what you would like to do is you would like to integrate this data by mapping the data from one of the ontologies, from one of the graphs into the other graph. And you want to do this by defining a mapping on the schema level, which transforms the graph on the one side into the structure it needs to have on the other side. And that is a non-trivial problem. And you need mappings to do that. You can't do that just by class-class relationship, because sometimes just the granularity of the graph is completely different. There may be reifications going on the one side, which are not on the other, for example. And one example here is the rule which you see down there, the 3 logical lines here. And this is out of a benchmark. The benchmark here is actually comes out of a complex alignment problem that we had to solve for an application that was in an ocean science context, the GeoLink benchmark, as it is called now. So we kind of solved the problem manually because we had to make, for some reasons, 2 versions of the same ontology, a more simplified one and a more extensive one. And we needed the mapping between the 2. So we made the mapping and afterwards thought, well, we could make a benchmark out of this. When we published this benchmark, I don't know, 8 years ago or something like that, some reviewers didn't want it published in the journal where he submitted it to, saying, this is too complex. None of the current systems comes even close to be able to do that. So, it's not a good benchmark. And we kind of said, that's kind of the point. This is a realistic benchmark, as opposed to the synthetic ones, which we have. This was a real alignment problem. So while this may be beyond our reach right now, right? We need to get this out because this is what we need to strive for. One of the things that go on in there, for example, is type violations, right? You break the logic in a sense, because some of these alignment rules, they map classes to constants, right? Or to controlled vocabularies, right? Things like this. So all this type of stuff is going on. But let me explain that rule just a little bit. You have two ontologies, yeah? There's a double implication arrow here at the end of the first line. And the first line essentially is a piece of one ontology. It talks about funding awards, right? And co-principal investigator here. And the other two lines on the other side of the arrow are predicates from the other ontology. And this is one of the mappings, one of the many dozen mappings, I don't know how many there were, which defined the complex problem, the complex ontology alignment problem. So, right, the state of the art in complex ontology alignment pre-LLMs was that essentially you couldn't do it. Any system that was around could solve complex ontology alignment problems only under very strong non-realistic assumptions, like, for example, a shared A box. Then you could produce the mappings, but that's not a realistic setting. That was before LLMs hit, and that's where we kind of left it back then. And then LLMs hit, right? Oh, by the way, we have a second benchmark which comes out of the enslaved ontology, which I just showed you. Similar thing there, a little bit more convoluted even in terms of the mappings, because the second one here has to do with Wikibase encodings of knowledge graphs. Don't need to go into detail here, but in any case, two benchmarks we have here. And now LLMs hit. And let me jump ahead a little bit. Let me skip a few things to this here. So what we gave the LLM as a problem was essentially a little bit simplified, because we wanted to give it something which, if it can solve it, it will help a human do the task and not kind of do it completely automatically. That was not necessary. So helping the human is our goal here. So what we did was, to just see whether it can in principle be done, is we gave the LLM the target, which was kind of the red part, the left-hand side of the rule, and asked which predicates should be on the right-hand side. And if it does a good job on that, then assembling that for a human, is not so complicated. So that's the task we gave the LLM. And if you do it like that, then you can look even at this as a precision recall problem. Kind of how many predicates do you get correct, and how many do you get that shouldn't be there? And our direct prompting, full ontologies, just didn't work at all. We got 5% of the predicates correct or something like that. So that just didn't work. We shoved the problem to the LLM, asked it to do it, and it didn't work at all. And now came on modules. So our ontologies, both of these ontologies are modular ontologies. Here is the GeoLink ontology, the modules. This is the module diagram on the top. So there were, I don't know, 15 modules or so, or a little bit more. Sorry, the top is the GeoLink. The bottom is the enslaved modules for the enslaved ontology, 15 modules or something like that. So what we now did was we did some structured prompting, very, very straightforward. We took the left-hand side of the rule, gave the LLM the list of module names, and asked the LLM, which modules do you need to see to solve this alignment problem? And it told us which modules it needs to see. And then we fed again the left-hand side of the rule together with the ontology modules it asked for and asked it to solve the problem. And it turned out it worked really well. Very naive, very straightforward, worked really well. Essentially, it's a divide and conquer. We help the LLM to focus on the part it needs to solve. And in this case, even ask the LLM to tell us which part it needs to do the divide and conquer. Two-step problem. Worked really well. Recall and precision is here by rule, right? So greater 0.75 means, for example, 3 or more of the 4 target rules predicates were found, right? And you see the values here. If you get 3/4 or more, these are the realms where having a human then to do the rest helps, because you have the schema diagram, so you get which part you need to look at, and you can assemble the rule relatively easily. So that was really cool. Now here's a curveball. That was some time ago, right? And when we recently did the same thing and asked an LLM to do it without modularization, it actually did really well. It did actually better than if we had the modularization step in between. So, something changed. And then again, the question is, what actually changed here? And the problem again is we have no idea, right? Well, we we fed the LLM the stuff when we did the initial tests, right, with the data, quite a lot. They've probably found the benchmark now and ingested it, right? So kind of that may have been why it now works, right? They may have found the module structure and that way solved it. So now we're getting a problem that we can't even do evaluations without making completely no problems, which are not out on the web. So we need a non-public benchmark, which kind of sucks. So the things are getting really tricky here just in evaluating this, because I don't think they will just do better now on large ontologies with complex alignment. I don't believe that, but that needs checking now because we're now getting these type of curveballs. All right, so I'm stopping here. Well, we did some other work where we also showed modules help. We looked into LM-generated ontology design patterns for ontology construction. The modular ontology engineering framework, Momo, Kogan, myself, also uses ontology design patterns central in their process. So doing that helps with ontology construction. There's more work going on, of course. And we also looked at LLM-based ontology population, where again, the modularization really helps. This is the Momo workflow. No time to talk about this. And I will just move on here and ask if there's more questions on this before I go into final musings. Ravi, please. Are you muted?
Yes. Can I ask the question?
Please go ahead.
Yes, I'm looking for ontology connection. And from whatever you described, Pascal, I see that predicate calculus is involved somewhat in better connections between ontologies. Is that a correct perception?
Well, it depends on what you mean by predicate calculus. Essentially, my view on ontologies here is that an ontology is formally constituted in its core by a set of by a logical theory. So, and of course you can do formal logical reasoning on that. So, that I don't know, you may mean this by predicate calculus, I guess.
No, what I was looking at,
okay.
Suppose I look at your modular diagram.
Right, okay.
And I look at ontology portion that you described in blue there.
Yeah.
And I look at another module and I see another blue.
Yeah.
How do these ontologies connect with each other? Do they
okay.
we have to go through predicate?
Right. So, we distinguish between different things here, and let me go to the enslaved one here, right? Which may be a little bit clearer. Essentially here, all the light blue stuff, because this is now an ontology, right? This is a kind of complete ontology, which means it shouldn't have anything open, so to say. So if I have the light blue here, like event up there, then actually there is an event module to be found somewhere, which is down here. So there's the event module. This thing up here is event, that's the event module. And we use this as a convenient way of drawing a diagram without having arrows going all over the place. Because if we instead would make another arrow from here down to event, and then do the same for all the blue stuff here, then nobody can read the diagram. So it's really a way to kind of keep things easier for the human to understand what was going on in the diagram. Now in the example we have here, we don't have that, and that is essentially so here we in the supply chain work here we did with NIST. we did not have a module for time or a module for material. But that simply is because what we did here was not make a complete ontology. Our goal here was to make key modules that could be used for supply chain issues. I hope that helps.
Yeah, but okay, we'll take the ontology to ontology connection as a separate question some other time, because I don't know if we have enough time for that
All right.
today.
Thanks a lot, Ravi. I will move on to just the last few things, and we have 10 minutes. So thanks a lot, Ravi, for that. And I just wanna tell you very generically about some musings here, and some which are not on the slides actually. First thing I wanted to mention was in the neurosymbolic realm, right? Kind of where does my thinking go right now? And right now everybody says agentic, right? So everybody has to say agentic because it's the hype thing. Which gives me flashbacks to semantic web services back then, right? And the original semantic web paper in Scientific American. And yeah, we may be getting close, but there's a but, and I'm going to come to the but in a second. So there is a really nice paper in Nature Human Behavior from last year where they looked at human AI teaming. And it was a statistical meta-analysis. So keep that with a grain of salt. It's a statistical meta-analysis, right? And nothing else, but also, it is that. Where they looked at human AI teaming and asked, when is human AI teaming really better than the human and better than the AI alone, right? Or when kind of should you rather have when should you rather have when does one of those actually do better, right? And the human AI team kind of performs worse. And what they found, and there's a lot of stuff in that paper, so really recommend to read that. But some top level results I found very interesting was if the AI is better than the human on the task, then the human AI team is usually worse, or is statistically speaking worse than the AI alone. Right? Now, you need to kind of swallow that. Yeah, the human drags the AI down. Now, if the human is better than the AI on the original task, then the human AI team is better than both the human alone and the AI alone, also statistically speaking. So, the problem being, of course, is you don't know upfront who is actually better at the task. Well, in many cases. And in cases where you could know it or have a good guess, agentic approaches usually don't talk about the human. They just talk about you distribute the system to agents. And I'm just saying, shouldn't the human be one of the agents here, right? And in particular, I believe one area where humans are just better than these systems is distributing the tasks. And that's kind of one of the things which kind of keeps growing on me, for example. So that talk about full automating. So I find that really very interesting. So I'm starting to think not neural and symbolic. I'm starting neural and symbolic and human. And for a lot of cases, in particular where quality counts, and it doesn't everywhere, right? Where quality counts, quality of the output, where it's safety critical, right? Or where any harm could be taken. That is probably where this becomes really important, and it should be thought of in a more principled way than is currently done. I see there's more questions. I may have some about the earlier topics, so I may be coming back to those because it's really only 2 more slides. So yeah, have a look at that. I found that really interesting. And the other thing I wanted to mention is we had a paper in Nature MI. Well, I was one of, I don't know, 30 authors or something on this. On comparing human and AI generalization abilities. And there is one piece there where it talks about things humans are often or usually better than AI. Things like compositionality, right? Breaking a problem into subproblems. Talking about generalizing from a few examples. Humans are usually better still. Dealing with noise, meaning shifts out of distribution data, that's all the things humans are really better than LLMs. And I think this is really interesting to think of in the context of human AI teaming. Last thought here, and then I'll come to the question. I was recently at a Darkstool seminar, which was rather interesting. I was very, very happy to be there, and actually one of the organizers. Although I was brought in there as a neurosymbolic person who didn't really know about the topic we were going to talk about, but it was too fascinating to say no. And it was about abstraction in humans and AI. And so we even had artists there. So we were really talking about abstraction. And one of the lead hypotheses I took out of this is that LLMs really suck at abstraction. At the type of purpose, there's a lot of aspects that are really important for abstraction, including ambiguity, having a purpose. As well, really solving something through ambiguity, for example. But there's also something going on, for example, in human communication or in composing a problem in our brains, right, into subproblems that work. And that is kind of, for example, finding an abstract perspective on the problem and on the subproblems where you can see that the subproblems will likely fit together on this abstract layer before you go down, making it more concrete and then see whether they really fit together. And something similar happens in human communication. We automatically adjust our abstraction layers, and language is a type of abstraction, right? Like our understanding of the world is an abstraction. We kind of adjust our abstractions on the fly until we reach something that is understanding, right? And now we're back to Habermas in a sense. And LLMs just suck at all that, right? So, which, fully automating of agentic AI, we'll see. I'm skeptical. All right, that's my musings. Back to the questions. We have 4 minutes. So I'll take the 3 which are here, and or the 4. So let me start with the last one. Purpose equals perspective, context. Not in the case of abstraction. The abstraction really is, an abstraction only makes sense if it has a purpose. Kind of abstracting for the sake of abstracting doesn't. But the purpose can be very, very different things. They can be, provoking an emotional response in the viewer to think abstract art, right? That could be a purpose. But abstraction, can also be much more tangible in purpose. Like, for example, language is an abstraction, right? For example, mathematical formalisms are abstractions. And in that context, it's important to differentiate between abstraction and generalization. But really, that's a different talk. Can't do that. I hope we'll have something written up at some stage out of the seminar. So yeah, Wojtek, regarding complex alignment, did you play with onto transformation patterns? For example, in your example, after transforming the first onto ontology by importing the agent role pattern, the ontologies might be alignable 1-1. No, we did. The answer is we did not, right? There's a lot of things to be done here. We got a little bit of a setback because suddenly the LLM can do our benchmarks. So our benchmarks kind of are almost useless now. So what do we do? There's more work to be done here. So the short answer is no. For Ankit, so for each domain or topic, we have to create an ontology module. Isn't a way to generalize all the domain into a particular framework. Otherwise, I think it's exploding. Okay, Ankit, I would need a full talk about the Momo approach. I suggest to read the paper, then email me, and Kogan, and very, very happy to discuss all that. So we have answers to this. The short thing is that, yes, I believe we need ontology module libraries, ontology sign pattern libraries. And that's the way to address the fact that most ontologies just don't get reused. Which is kind of counter to the original idea why ontologies were created in the first place, so to say. Sorry, can't go in detail. I have 2 minutes. Harshit, when you projected a symbolic domain into a predefined ontology, does the resulting presentation preserve enough structure to reconstruct the original input using the same LLM? I have no idea. Maybe an interesting thing to try. I need to think about this one. So thank you. Gary, it might be interesting to consider if what we identify as system 1 or system 2 makes humans better at some things. This may vary by the nature of the domain problem, worth a look, perhaps. Agreed, Gary. Yes, absolutely. I think this is one of the things which really promises to go forward, understanding better what humans can do and what LLMs can do. And that brings me back to saying we need more published works on what LLMs cannot do. and which brings us back to the old science problem of publishing negative results, right? Big bag there. And I'm stopping here and back to the organizers because we're out of time, I believe. Thank you very much and happy to follow up. You can join the Neurosymbolic Slack if you want. Catch me there. That may be a good way to do that. And if you don't know where the Neurosymbolic Slack is, send me an email. I'll get you on.
Well, Pascal, on behalf of everybody, I want to thank you very much for something that will keep us thinking for weeks. And so you may be getting some more messages on the follow-ups on this.
Absolutely. Putting my email in the chat. Feel free to email. I'll try what I can, do what I can, or email me there if you want to get a Neurosymbolic Slack where you can also find me as about.
And you've already had a series of presentations on Neurosymbolic, and your Slack channel allows you to understand who's presented what and maybe access it, right?
Right. I think it's also good crowdsource, right? I mean, it's not a terribly active Slack. A lot of things go on there in private channels. But, use the crowdsource there. I mean, there's 1,300 people, over 1,300 people on the Slack, right? So if you kind of post to the general channel there and ask, what are good pointers to get started or for presentations, videos by other people, you'll get responses. You get at least one by me, right? And then others will probably chime in as well. So that's a good use of the Slack.
Okay.
All right.
Thanks
Maybe
a lot.
we'll cross-post some things to Ontolog Forum.
Yeah. Just wanted to thank you so much and also make a musing comment that depends on the human, the expertise level of the human, doesn't it?
Sorry, which part?
Uninformed human like me and informed human like Pascal.
Yeah. Well, yes. Yeah. But see, the other problem is the following, and that's the issue, right? So let me put it that way. I'm getting these questions sometimes through some channels by people in, whatever, administrative offices, for example, saying, I want to use an LLM for X, how do I do that? And then my first response is always, if you don't know what you're doing, don't, right? In particular with LLMs. Because, if you don't have a human who knows what's going on, everything can happen. And in particular, you don't have any guarantees, right? So that's part of the thing here. And I think, society will probably learn this before disaster strikes, but, yeah. All right.
Thanks again, Pascal.
Thank you.
Thanks again, Pascal.
Thanks.
So at this point, we will adjourn, and I hope everyone will come next week when we are going to start, have the last actually session in the AI and ontologies track.
Yes, and I believe
Gary,
there will
can
be
you
two
say it a little bit?
speakers. Ram has organized it with 2 speakers, I believe.
Great. And with that, we'll adjourn. And thanks again to Pascal and Gary and everyone else.
Thanks
Bye
a
now.
lot.